Okay, great. All right, so this particular lecture is about foundations of clustering and dimension reduction. So in the, I would say in gene expression profiling, because we're always dealing with high dimensional data, right? The total number of genes being 20,000 or 30,000, or, kind of depending on the platform you use to generate the data and the pipeline you use to kind of pre-process the reads. And given such high dimensionality, usually it is, well, impossible for anyone to be able to just sort of visually inspect the data and derive meaningful interpretation. And hence, some kind of automated analysis is always needed. And clustering and dimension reduction has been two of the, I would say, most popular and most routinely performed analysis on gene expression datasets. So speaking of clustering and dimension reduction, I want to sort of take a step back and quickly talk about a higher level concept that's called unsupervised learning. So in general, in machine learning, people can divide kind of the whole machine learning field into two broad areas. One is supervised machine learning, and the other is unsupervised learning. So the big difference is that, in unsupervised learning, what we have is a high dimensional data sets with, for example, rows being features, genes in our contexts, and columns being samples. These could be different patients in bulk RNA-seq data. These could be individual cells in single-cell RNA-seq data. So given such a data matrix, if this is the only thing we have and we're trying to make sense out of it, right, to get clusters of cells or clusters of patients, then this is in general unsupervised analysis. And for supervised analysis, the paradigm is, or the framework is, in addition to this data matrix, we also have a vector here containing descriptions of individual samples we have. For example, some of these columns, some of these samples could be cancer patients, and the other columns could be normal subjects. And once we have these, say, 0, 1 labels for these columns, for these patients, then we can ask, we can think about constructing models for to classify them, right, to distinguish them. And any machine learning analysis that utilize both the raw data, high dimensional data itself, plus additional class labels, this is called supervised analysis, because the analysis is supervised by the fact that we know these class labels of, say, 2 different patient types, or maybe multiple cell types, if this is single cell data and we have cell type labels for each cell, right? And under unsupervised learning, well, there are kind of 3 different types. One is clustering analysis. For example, we can cluster, again, the cells here, the columns, into different cell types. We can also talk about trajectory finding or trajectory inference. And this is about, what if the cells here, they do not form distinct clusters, but instead they form some kind of trajectory that represents the early stage, intermediate checkpoints, and late stage of a certain biological process. And a certain cell may be, at the early stage, or maybe halfway through, or maybe at the end stage, right? So how can we connect these cells in the high dimensional space so that we draw a kind of a line, a winding trajectory in the high dimensional space that represents the biological progression where these cells were sampled from. And trajectory analysis can also be framed in the context of bulk RNA-seq. For example, maybe all these columns, these samples, they're all cancer patients. And then some cancer patients represent an early stage of cancer development. Some of them represent, say, late stage, and some of them represent intermediate stages. Then maybe there's a possibility to create to extract a trajectory that connects these patients so that this trajectory represents cancer development, right? And a third example about trajectory analysis is that this trajectory among patients or samples can also be artifacts. For example, one analysis that I did very long time ago was a gene copy number data set derived from cancer patients, and it turns out that while those cancer samples, when they were taken from the patients, different samples have different level of normal contamination. So some cancer tissues that were taken is 90% normal and only 10% cancer cells, so heavily contaminated. And some are purely just cancer tissue, right? And when I applied trajectory analysis to those data set, I get a very nice trajectory. And on one end, it is sort of 0% contamination. On the other hand, and is 100% contamination or 90% contamination, and in the middle is 50%, right? So a trajectory can also reflect some technical variability that has the sort of the continuum nature, right? So when you have a data set at hand, right, if you want to apply clustering analysis or trajectory analysis, then well, very often, one of these two types of analysis is going to be more appropriate than the other, depending on how the data looks, depending on sort of the geometric property of the data. And this is actually a topic that I'm going to touch upon in a later lecture, actually tomorrow's first lecture, on geometric properties of high-dimensional data in the context of single cell. But in the context of bulk, such geometric consideration is also useful. Okay, and then the last sort of third unsupervised learning type of sort of analysis is called dimension reduction / visualization. And this is, I would say, somewhere in between the first two, or I mean, it is an exploration that does not really have a preconceived notion of how the data look like, right? So we just take the data that's in high dimensional space we cannot see. So let's reduce the data into two-dimensional space in a meaningful way so that we can see the data, and then whatever we see is our interpretation. If we see clusters, it's clusters. If we see trajectories, it's trajectory, right? But of course, exactly how we do that dimension reduction will, in some sense, influence what we will see. So, and that's why, when we are performing, or later you guys, right, are playing with dimension reduction tools, it is, I think, important for you to understand some of the basic concepts behind these dimension reduction tools. What kind of information are they trying to preserve? What kind of information they actually will mess up when they do dimension reduction? But those are probably viewed as, unnecessary information to be kept, and hence maybe it's okay. In certain cases, maybe it's not. Okay, so in this lecture, I'm going to cover a few clustering algorithms and a few dimension reduction algorithms, and trajectory finding will be left to, well, tomorrow morning's lecture. All right, so one big challenge / issue for unsupervised learning is that usually there doesn't really exist an underlying ground truth. For example, given a data set like how many clusters there really are, right? It really depends on, well, the answer actually is subjective. It depends on how hard you squeeze your eyes, right? If you look really closely, you see many clusters, but if you say zoom out and take a bird's eye view, you probably will see fewer, right? So in clustering analysis and also the other two types, usually a ground truth is really not really well defined. And therefore, well, that's sort of the sad reality, right? There typically isn't a ground truth that we can kind of aim for. If we get it, we get 100% right? And also, even if there exists a ground truth, usually it is impossible for any algorithm to say guarantee that it always gets the right answer with a fixed set of parameters. So you always have to tune your parameters, and then really what is the right answer, what is not the right answer, right? It's very hard to implement. So in my opinion, the set solution about validation for clustering analysis is that people typically leave that validation to downstream analysis. Okay, so it's sort of sad for the clustering step itself. It is unable to justify itself, and it requires some downstream, usually biological interpretation to justify. For example, if we cluster cancer patients into 4 clusters, and later we look at their survival outcome, and one of those clusters really has much better survival outcome than the other 3, for example, then that would be one way to validate the clustering result, right? Or if we're clustering, say, single-cell RNA-seq data, right? Here, columns are cells into cell clusters, and then later we see that different cell clusters, they exhibit different cell type specific marker genes that we already know in the literature, then that will be a nice validation that these clusters, they really reflect different cell types, and hence great clustering, well done, right? But of course, usually if you modify your clustering analysis a little bit and you get one more cluster or one fewer cluster, it is very likely that you're still able to interpret in your downstream analysis, interpret your clusters really well. So for clustering analysis or unsupervised analysis in general, as a computational person, my goal is that I want to get the analysis sort of about right so that it can reflect good amount of biology in the downstream validation. But then, if I really want to, get my analysis somewhat 100% right, defined by whatever criterion, it likely will be a rabbit hole that doesn't have an end. So anyway, that's kind of a general introduction of unsupervised learning and its 3 manifestations in the context of gene expression profiling and also the sort of the challenges associated to it. Now, in this lecture, what I want to do is I want to quickly go through 5 different clustering algorithms and also 5 different dimension reduction algorithms so that I hope afterwards you guys will have a general sense of how these algorithms work in general and in what scenarios each algorithm may perform better than the others because of kind of the way they're designed. So let's start with the first one, the clustering algorithm. So hierarchical clustering is, well, arguably, I think the most popular clustering algorithm that has been applied to gene expression data analysis. So here is just a random heat map that I grabbed from a Google search, where each row, this is a gene expression data matrix, where each row is a gene or a FA matrix probe, and each column is a sample. And these rows and columns are organized by hierarchical clustering, and the hierarchical clustering results are shown here. Okay, so you can cluster the rows, you can cluster the columns, and these both will induce this hierarchical tree and also induce an ordering for you to reshuffle your matrix in a way that similar columns are next to each other, similar rows are next to each other, and then you see these blocks that you can use to interpret. For example, these strings, okay, collectively, they serve as maybe marker genes for this group of patients, right? And now, just very quickly, the algorithm for generating such hierarchical tree, well, is actually a very simple algorithm. Let's say if we're trying to cluster patients, okay, then we start with a initialization where each patient is one cluster by itself. So each patient is a singleton cluster. And then we repeat the following. So among all the clusters, we find the closest pair of clusters, and then we merge them. Okay, so if we have 100 patients to start with, we look at their pairwise similarity, find the 2 that are most similar to each other, and merge the 2 into one cluster. So now we have 99 clusters. One cluster has 2 patients, the rest 98 are singleton clusters, each has only 1 patient. But now we have 99, we can repeat the process. Among the 99, find the 2 clusters that are closest to each other, and merge them so that we have 98, and we keep going until there's only 1 cluster left, and that will give, and each merge is sort of one binary split here. And all these merges collectively give us the tree, right? And the key point here is, of course, how we define, similarity, right? Closest, and also how do we define similarities, not just between 2 individual data points, but 2 clusters. Okay, so in terms of what defines close, what defines far away, popular distance metrics are L2 distance, for example, the Euclidean distance, and L1 distance, sometimes it's called the Manhattan distance, and also the correlation distance. Okay, so in your own practice, which of these distance metrics you should use, it really depends on your understanding of what is more important consideration to define similarity. For example, if you have data sets where, say, 2 samples are not very much normalized, and their correlation, if the 2 samples are highly correlated, you will consider them to be very similar, even though numerically these two vectors are not exactly the same. They have different scales, for example. In that case, correlation distance would be very useful. But in cases where your data is very well aligned and normalized, Euclidean distance is, well, my optical choice. Well, in fact, when I try to cluster genes, okay, I usually use correlation distance because certain gene may be highly expressed across all samples, and certain gene may be relatively lowly expressed. But then if they covary, it means that they go up and down at the same time, and maybe they're involved in a common pathway. So then in that case, correlation would be more important. In the case of clustering genes, where different genes have different sort of baseline expression level, then correlation would be a more meaningful distance than Euclidean distance. Okay, but when I cluster samples or cluster cells, then I usually go with L2 distance because samples usually are kind of pre-processed using various normalization techniques so that they are well aligned. Okay, so that's a choice of distance metric. Oh, and sometimes I use L1 because L1 does not involve taking squares and square roots, and that calculation is faster. So when I look at especially single cell data where I have millions of cells, then computing Euclidean distance between two cells is going to be kind of a maybe 0.0001 second faster than slower than computing L1 distance. But if I have millions of cells to process, then that little bit of gain could translate into a large amount of time saved. So that's, at least in my own experience, why I would choose L1 over L2 sometimes. All right, so in terms of computing the distance, now we have the distance metric defined. Now, how do we define the distance between two clusters of data points, right? So if each cluster is only a singleton, then it's easy. It's just a simple distance. But if we have two sets of points, A and B, and A has 10 points in it, B has, say, 5 points in it, then there are multiple ways that we can define the distance between these two sets. So one idea is called single linkage. And this is basically looking at the pairwise distance between the 10 in set A and the 5 in set B, so 50 distances, compute all of them and take the minimum. Okay, so then that is the sort of the closest or the smallest gap in between these two sets. And that's called the single linkage. And the idea of complete linkage is just, again, those 50 numbers, you take the max. Okay, and that represents sort of the diameter of the set A combined with B. Okay, the union of the two sets. The diameter of it is the complete linkage, and average linkage is basically those 50 numbers you take average. And Waltz linkage is something that's more complicated. It basically looks at the scenario where your set A and set B are separately modeled by different means. What would be the variance we'll see? And if we model set A and B's union as one set, then how much variance we will see? And the gap in between them will show us how far away set A and B are. So the Waltz linkage is, I would say it behaves somewhat similar to average linkage. And in my opinion, I actually don't really know why Waltz linkage is more popular than average. But in practice, I see more people using Waltz linkage than average linkage. Okay, so now that we have the distance metric discussed and the linkage discussed, and now we have, and once we make our choice of what distance metric we use and what linkage we use, now we have basically the hierarchical clustering algorithm completely specified, and we can run the algorithm to generate the tree structure. Okay, so now how do we choose these? I've already sort of touched upon how do we choose distance metric, but then how do we choose among these linkages? Okay, so in general, I would say that if we're dealing with an easy clustering situation where our data form compact and well-separated clusters, so this is an easy case, then all those linkages, they are equally good. Okay, and it doesn't matter which one we choose, we're always going to get a well-balanced hierarchical tree where each major branch corresponds to one cluster that we hope to catch. Now, in real data sets without clear cluster separations, then choice of linkage actually matters. Okay, so for example, let's say if we have 3 clusters looking like this, okay, And two clusters are big with very small gap in between, and we have a small cluster that's a little bit further away. If we're doing single linkage, then the distance between these two clusters is very small. The distance between these two clusters is this gap. This is a bigger gap, right? So single linkage will view these two clusters as the most similar and then group them first, and then group this cluster next, okay? But if we go with complete linkage, okay, so in terms of complete linkage, the distance between these two clusters is from here all the way to here, okay? So this is the distance between these two big clusters. But if we compute complete linkage distance between these two clusters, is still the diameter is from here all the way to here. And in cases where this cluster is small, then it's very much possible that these two clusters are first merged, and then this cluster is merged later. Okay, so now and these two sort of choice of linkages, they actually give you sort of potentially can give you completely different hierarchical clustering tree structures. Okay, so in cases where, say, you want a relatively more balanced hierarchical tree, okay, then I think complete linkage is actually the linkage choice that tend to give you balanced data because it's using sort of diameters to define distances. Okay, so if you use complete linkage, then number of cells under kind of each split on either side will be relatively similar. But if you use single linkage, then it's you don't have that property. And single linkage analysis very often tend to give you staircase-like hierarchical tree that you have, for example, here, right? And another merge with a tiny cluster, and another merge with a tiny cluster, this kind of staircase. And usually in hierarchical clustering analysis, you don't really want to use single linkage because the tree is very much unbalanced, tend to be unbalanced. But in trajectory analysis, where you want to find, say, a progressive changing trend that help you to connect the dots, then single linkage is actually a very good choice. So very early on in the field of trajectory analysis, there was this proposal actually from one of my early work, which used minimum spanning tree to connect the dots, to connect different clusters, and use the structure of the tree to represent the underlying progression. Okay, and minimum spanning tree is actually equivalent to single linkage hierarchical clustering, and because it's trying to basically find very small gaps in the data to sort of make those edges and connections, it is able to help you to map out kind of how things progressively change. Whereas complete linkage, well, that sort of balanced structure doesn't really give you that progression. Okay, so if you are more focused on identifying progression and trajectory, single linkage is better. If you really want a highly balanced tree, so because maybe you have limited sample size, right? You want, say, different splits to give you roughly equal number of samples for you to do subsequent statistical analysis, then complete linkage will be the one that tend to encourage balanced tree. But of course, you can I always start with the other two, the average linkage and worst linkage, because they behave somewhere in between. And then I will look at, you know, those two algorithms, are their resulting hierarchical tree satisfactory and interpretable? If yes, I'll stop there. If I'm not happy with them, then depending on, you know, how, you know, why I'm unhappy about those results, then I would move to either single linkage or complete linkage. Okay, so that's kind of my thinking process when I do hierarchical clustering on gene expression data. All right, so well, there are a lot to cover, so I am a little bit fast. But well, good thing is we have this lecture recorded. All right, so let's move to the second topic, k-means. Okay, so k-means is I would say the second most popular algorithm in clustering analysis in gene expression, in the context of gene expression profiling, and also in many other contexts. The algorithm for k-means is also super easy to discuss and implement. And when we perform k-mean analysis, right? So we have a bunch of data points. We want to break them into k clusters. And in order to apply this algorithm, we as the user of the algorithm, we have to specify what k we want. Okay. So we have to specify k equal to 5. I want 5 clusters, or whatever. And once we've specified k, then the algorithm would initialize itself with random cluster centers. Okay, these could be, say, k random data points out of all the data points we have, or just k random points in the space where the data resides in. And then a k-means would repeat the following process into convergence. So first, it will perform an update cluster assignment. So this is by computing the distance between every data point and every cluster center, and then assign each data point to its closest cluster center. And then after that, once we have the cluster assignment, we can update the cluster center by taking all the data points assigned to the same cluster and take their average, find their center, and that's the new cluster center for each cluster. And we just iterate until the cluster assignment does not change anymore. And once the cluster assignment doesn't change, of course, mu will not update, and this algorithm will converge, and nothing more will happen, even if we keep iterating. So that's when we stop. Okay. So k-means is very easy to implement, but of course, it has many kind of subtle issues that people need to consider, and also people have developed many variations of it. So, for example, k-means is actually an algorithm that that has many local optimal. So if you run it multiple times, because the initialization is random, it is possible that the algorithm will converge to different solutions, especially when your data does not have very clear cluster structure, right? So actually, again, if your data is super clear with a small number of clusters, and that's actually the k you choose to use, okay, and these clusters are well separated, then even if you run k-means like 100 times, 1,000 times, I can guarantee that 99.99% of the times you get the same solution, which is the one that's reflecting the underlying structure. But if you are dealing with a more difficult clustering problem, where say you have a peanuts, right, representing 2 clusters touching each other, but not well separated, then when you run k-means many times, then I can guarantee that you're gonna see that the solution out of each run will not be exactly the same. And then one solution, and then one kind of approach that people develop to address that is, let's actually embrace that randomness and run k-means many times, and then find a consensus among many runs of k-means. For example, you can say 2 data points. If among all the 100 runs, right, 90% of the time, these 2 points are in the same cluster. So then I'm confident that these 2 points belong to the same cluster, right? But for 2 points, if it's 50-50, then I will say that I don't want to put them in the same cluster, right? So that's the idea of kind of a consensus k-means. We run it many times, we find a consensus. However, okay, at least my own opinion about this, you run k-means many times versus, and you look at each solution versus you look at the consensus solution. Each of them is sort of a possible solution out there that is sort of not too much better or worse than the others. So in my own practice, I usually actually only run k-means 2 or 3 times. And if I see that they roughly agree with each other, although there are some randomness, then I will say, among these 3 times, I'll trust any one of them. Okay, but if I see that I run it 3 times, 5 times, and I see drastic difference, then I probably will say that I don't trust any of them, and I want to use other algorithms instead of k-means. Or I want to pre-process my data better, or maybe I'll just blame the data and say this data just doesn't have strong enough of a cluster to be discovered. Of course, there are also other possible caveats of k-means, but that's kind of my general first step and my kind of first gut feeling. All right, And also when running k-means, cluster can disappear. For example, if one center is somewhat unlucky, initialized in an empty void, then algorithms, implementations of k-means typically will just drop it or reinitialize and run it again. And also k-means has one big caveat that it is more designed to capture clusters that are of a round shape. Okay. And for clusters that have arbitrary weird shapes, k-means may run into problems. For example, let's say if we have a data set look like this on the screen, and there are two clusters indicated by the colors, but then these two clusters, neither of them is a round shape Gaussian ball, right? So now, even if you initialize your algorithm with the right cluster, okay, what's going to happen is, let's say all these points belong to the cluster, one cluster, all these points belong to another cluster, and if you compute the center of the first cluster, the center is here. You compute the center of the second cluster, the center is here. You do reassignments according to Euclidean distance, and things all get messed up, right? And now this actually would be a scenario where the data has clear cluster structure, but then running k-means will not give us good solution. If we run it many times, then maybe randomly we'll get different solutions. So then, blaming the data is not the right way to go, right? Maybe trying some other algorithm is appropriate. And this actually sort of also is an example where I want to take a step back, okay? So when I have a new data set that I'm playing with, I have maybe some assumption that I think one algorithm should work. I apply the algorithm to the data, I get very bad result. Then what I do, right? Should I blame the data or should I blame myself, my choice of the algorithm, right? Both are possible. So usually I blame myself first and try some other algorithms. And for example, I know this is a possible reason why k-means wouldn't work, right? So I try some other algorithm, and after I try maybe 2, 3, 4 different algorithms that cover possibilities that I can think about, and if none of them work, then I'll go and blame the data. All right. So I guess for you guys, who are biologists, you generate data, you send it to someone, and someone and that person come back and say your data is bad. You should ask him or her, like, what algorithm have you tried, right? If their answer is only one algorithm, then you may, push back a little bit, right, and say, maybe can you try more? All right. So so that's the caveat about k-means. And also, let me actually skip this because this is the randomness and deterministic k-means is actually a pretty long discussion. But I want to spend some time to talk about the last point, the number of clusters. When we run k-means or other algorithms that require us to specify what is the number of clusters we want, then we, as the user of the algorithm, are responsible for setting that number, right? And we should try to set the number as close to the right number as possible, or in the sort of roughly the right range, okay? And my favorite algorithm to use to determine a proper range of k is something called gap statistics, okay? So here is a algorithmic description of gap statistics, but I don't really want to read it. I'll go through it with you using a real example. And by the way, this slide is a MATLAB script implementing the algorithm here, okay? So you have the pseudocode, you have a real code in MATLAB, and well, let's look at kind of a data example to go through what gap statistics is. Okay, so now let's say we have a real data set that has 3 clusters. So this is an easy case, right? And then one thing we can do is that we can try to cluster this data with k-means by choosing different k, right? If we choose k equal to 1, then it's trivial, it's just everything is one cluster. If we choose k equal to 2, then maybe the algorithm will say this is one cluster and the combination of the other 2 is another cluster. If we choose k equal to 3, great, we get the right answer. If we choose k equal to 4 or larger, then some of these clusters will be broken into small pieces, right? So that's so we can try different k on this real data, and for each choice of k, we can compute this w here. Let's go back 2 slides. So this w quantity is basically the pairwise distances of all data points that belong to the same cluster. Okay, So here you see that I and J, they belong to the same cluster number K, and we sum up all the cluster. So this W quantity, roughly, it helps you to quantify the volume of your cluster, okay? So when K equal to 1, everybody is in the same cluster. So this W quantity roughly describes the volume or the area of this triangle, okay? And then when K equal to 2, this W quantity represents sort of this area plus this area, okay? And when K equal to 3, the W quantity represents the volume of these 3 clusters. And when K equal to 4 or larger, the W quantity will roughly still represent just the sum of these 3 areas. So that's why when we plot, say, WK over the first W, so we normalize a little bit, we see that there's a big drop, a quick drop to the right number of clusters. And then after that, it's still going to be dropping because we're still dividing, but the drop is going to slow down, okay? So this is how the first curve is generated. And then the second curve here, well, this smooth curve is generated by, we take a random version of the data that's uniformly distributed in the space where the data resides in, okay? So when we have this random data, we can also do k-means with k equal to 1, 2, 3, 4, 5. And we'll see that as we increase k, the volume will also keep reducing, okay? Because we're dividing, and always this will only reduce, right? But now when we have the smooth curve from the random data, and we have this curve from the real data, we can put these 2 curves together in one plot and then take their difference. And that's the gap in gap statistics. And when we take the difference, we see the gap. And it turns out that for this particular case, K equal to 3 give you the largest gap. And K equal to 3 is also intuitively the right number of clusters, okay? So this is sort of a validation that gap statistics tend to be able to suggest the right cluster for you. In reality, of course, when you do this, the gap in between the 2 curves will likely not look this great. Maybe it will look smooth with a plateau. Maybe it will increase and then smooth with a plateau and then gradually go down. And then that means in this plateau region, there might be multiple different choices of Ks that seem to be equally good. And in that case, exactly which K we choose, I would say I will try them all and then use subsequent interpretation to help me to decide which one I want to use, or I would just randomly pick one of those Ks and go with it. Okay, so
there's a couple of questions in the chat you might want to look at.
Okay, all right. Let's see. Is this similar to cross-validation score? No, this is not similar to cross-validation. Cross-validation is an idea that's usually used in supervised analysis, where you use the known class label for some left out samples that you did not use to validate your modeling and your parameter choice, okay? So here, on the way that we are deciding our parameter choice, actually we use all the data we have. So this is not cross-validation. All right, so another example of supervised versus unsupervised learning. Let's talk about that later. Well, which is the best metric to decide which K to use on unsupervised? There are multiple algorithms out there to help you to decide the number of K. My go-to algorithm is gap statistics. This is the one that I trust most, but there also are other algorithms. For example, you can look at within cluster distances and between cluster distances and use that ratio to help you to know whether different clusters are well separated. And that's, I think, an algorithm or score that's called Slewit score. And that's another popular choice people use. The bottom line is that, I think in data sets where there is indeed a sweet range of a property K, different algorithms should all point you to roughly the same range. And in cases where different algorithms give you drastically different answers, then maybe it's because like caveats of k-means, right? Or maybe it's because really we should reconsider whether clustering is the right algorithm to apply to that data set. All right, so is there a way to use eigenvalues to determine the number of K? There actually is, and that's in, well, one of the next algorithms that I'm going to talk about. All right, so I think I've covered at least half of the questions, and let's move forward. So with this example, I hope that you guys now understand at least how gap statistics works. And later, if you have access to MATLAB, you can try running this script, which will reproduce the figures on the next slide. And you can also kind of play with different scenarios that you want to simulate. All right, so about eigenvalues, right? There are two clustering analysis algorithms that one is called spectral graph analysis and the other is called community finding. So these two algorithms, both of them, they actually involve eigenvalue in some sense. Okay, and I grouped these two together because both of them, they operate in the same, in a similar way. Both of them, they require us to, or the algorithm to first construct a graph connecting data points that we want to cluster. And in that graph, each node is a data point we want to cluster, and each edge represents the similarity. So there could be weight on each edge, right? So for two nodes that are really far away from each other, maybe we don't have an edge connecting them at all, or we have an edge connecting them, but with very, very small weight. And then once we have this graph, we can talk about how we can cut this graph into smaller pieces by removing minimal number of edges or disrupting minimum amount of weights. Okay, so to construct weights, there are different formulas, but in general, what we want to do is for two data points that are very similar to each other, we want the weight to be large. For two data points that are far away from each other, we want the weight to be very small or just zero so that the edge doesn't exist. Okay, and once we have this, then the spectral graph partitioning algorithm, what it does is it takes the weight matrix, okay, and construct a matrix that's called Laplacian, and then compute its eigenvalue and eigenvectors, and use the eigenvalue and eigenvectors to do clustering. Okay, so here is one example. Let's say we have a bunch of nodes, data points we want to cluster, 10 of them, and let's say the weights are defined to be just 0 and 1. Right? Similar nodes are connected with a weight 1 edge that has weight 1, and far away nodes are just not connected at all. Okay, so then this is our W weight matrix. Okay, in other scenarios, you can actually use any real number between 0 and 1 to define the weights on any sort of edge. Right? So this is just kind of a binarized, extreme simplified example. Now, once we have this A matrix, this weight matrix, construction of the Laplacian, okay, let me flip a train. It's just negative of the weight. And then we make the diagonal elements in a way that the column sum is all 0, okay? And then once we have this Laplacian matrix, we take its eigenvectors and eigenvalues and something magical would happen. Okay, so first of all eigenvalues are non-negative, and there is one that's exactly 0. You see a negative sign here. This is numerical imprecision. Okay, so one eigenvalue for sure will be 0, and this is because how we construct the diagonal elements to make the column sum to be 0. And then if we look at the second smallest eigenvalue and its corresponding eigenvector, so what's magical is in this eigenvector, the elements that all have negative sign versus the elements that all have positive sign actually induce a partition of nodes into two groups. 1, 2, 3, 4 is one group, the rest is another group. And if you look at the structure of the graph, that corresponds to a cut here, the most appropriate cut that cut the graph into two pieces that remove the least amount of weights. Okay, so this actually echoes one of the previous one of the questions in the chat. So there actually is a way to use eigenvalue and eigenvector to suggest a cut to divide a data set into two clusters. Okay, and well, this is sort of the example showing that, right? And now here is another example where there seem to be multiple different ways to cut the graph into two pieces. And again, only one eigenvalue is 0. The second smallest one, if we see its corresponding eigenvector, so 9, 8, 9, 10 are negative, the others are positive. So it's actually suggesting a cut here, okay, which also is a pretty appropriate cut, right? And these values are very close to 0. This reflects the fact that these 4 actually could go with these, right? So if our weights is not 0 and 1, then there might be a little bit of bias that will encourage these to be grouped with, either the upper P triangle or lower triangle. But anyway, this is another example showing you that the eigenvalue and eigenvector analysis is able to do clustering for you. And now one question is, what if we start with a graph that's already disconnected? Then what you will see is that you will see more than one eigenvalue being exactly 0. So if you see this, that means your graph is already disconnected, and then you should just apply this algorithm to each piece separately and iteratively. Okay, and in fact, spectral graph partitioning, because the fact that it can only cut or divide your data into 2 clusters, is often applied in an iterative way. So you have a data set of 100 data points, you apply this once, and then you have 2 clusters. One has 80 data points, the other has 20 data points. And then for the 80, you can run the algorithm again to divide into maybe 40 and another 40. And for the 20, you can also apply the algorithm to partition the 20 into 2 pieces, right? And of course, you can do it all the way to the bottom where you end up with singleton clusters. So you have a full binary tree generated in a top-down manner, or you can have some stopping criteria and say that the smallest size of cluster I want is 20. So then if you have a cluster of 20, then you don't want to partition anymore. Okay, so spectral graph partitioning, people usually apply that multiple times and with some stopping criterion to get X number of clusters, and the number of clusters is determined by the stopping criteria. All right, so community finding is an algorithm that, in my opinion, is better than spectral graph analysis because it is able to automatically suggest number of clusters to you, but it is also more difficult to implement because it's operationally, the optimization is very difficult to perform. So the process of community finding is very similar. First, we have that graph with all the weights in between data points. And then what we can do is we can suggest a cluster assignment, okay, indicated by the C here, and then compute this Q quantity, which is called modularity. Okay, so what this Q quantity represents is that for, say, data points I and J that belong to the same cluster, okay, they want the weights to be much larger than what we would expect by chance. And for cases and for data points that do not belong to the same cluster, this Q quantity does not worry about them at all. Okay. So in essence, what this Q quantity is measuring, like for a cluster solution that we propose, do we see more connections within each cluster than by chance? Okay. Now, and that's what this Q quantity is about. And by the way, implementation of community finding, there is a very good implementation by the Google Code community. So if you just Google search Google Code community finding Louvain, which is the name of a popular community finding algorithm, you will see implementations there. And existing single cell analysis packages like Surret and ScanPy, they also have implementations just sort of packaged in those algorithms. All right, so here, this is the same example. We start with our weight matrix, and if we suggest the right solution, okay, where the first 4 is a cluster, the remaining 6 is a cluster, then the Q quantity it's actually very easy to compute. This is just one line of MATLAB code. The Q quantity is 0.33. But if we suggest incorrect clustering solutions, for example, if we want to break this into 3 clusters this way, or we view everybody in the same cluster or everybody as a different cluster, we always get a lower modularity. So this is giving you a few examples showing that incorrect or inappropriate cluster solutions compared to this more appropriate one, inappropriate cluster solutions will give you lower modularity. Okay, and here is another example, right? There should be 3 clusters, and a 3 cluster suggestion give you the highest modularity, 0.36, but the other possible suggestions all give you a lower, okay, lower Q or lower modularity. So these examples are all intended to tell you that optimizing or maximizing modularity by finding a cluster solution usually will give you a good cluster solution with a proper number of clusters. Okay, but so far I actually have not really told you how to search the possible cluster assignment space to find the right solution. Okay, and that is actually in computer science, this is an NP hard problem. So that means if you have, let's say, thousands of data points you want to cluster, and you want to optimize this queue by finding a clustering solution, your computer probably need to run 10 years to find a solution for you. Okay, so in reality, what people do with existing algorithms like Louvain algorithm that I just mentioned, and another algorithm that's called Leiden. So these algorithms, they all use greedy heuristics to do greedy merging, and they have some resolution parameter that you can tune to encourage, say, different number of clusters. Okay, so all existing algorithms, they are trying their best to optimize Q, but none of them is really able to find the solution that really truly maximizes this modularity quantity. Okay, so again, sort of the sad reality is, although this algorithm is able to theoretically suggest the right number of clusters for you, but still in practice, it is still us, the users, using a certain resolution parameter to control how many clusters we will get. Okay, so maybe in the future, 10, 20, 50 years from now, when we have quantum computing, so that NP hard is no longer hard, then maybe this would be the algorithm that truly is able to give us the right number of clusters. All right, so finally, density-based clustering. Okay, so this is an actually, well, not just one algorithm, there are multiple algorithms. So the most famous density-based clustering algorithm was published, well, more than 20 years ago, and have accumulated thousands of citations. But in general, what they are doing is they say, okay, so we have many data points, right? And then for each data point, they will define a neighborhood, a small epsilon neighborhood, and count how many other data points are in this neighborhood so that we know the local density of each data point. Okay, and then what we can do is, or what this algorithm does is, they will say for data points that have the highest local density. So for example, if I'm a data point, my density is 100, and all my neighbors, their density are lower than me, then I will become a cluster center. Okay, and then all my neighbors, okay, who kind of look up to me, right? Because another data point is my neighbor, and his or her density is slightly lower. But then because we are neighbors and that point knows I have higher density, so that point will kind of look up to me, and then that point will just join my cluster. Okay, so you can just think of this as really you're looking at a very hilly area, and each hilltop is one cluster center, and then and that cluster center just sort of propagate downhill so that each hill is kind of painted by the cluster assignment of the hilltop. And then when it comes to the valleys, their assignment will be relatively random. And some algorithm will just try to assign a cluster label for every data point. And some algorithm will say that in the valley area, right, the density is so low that they will say, we don't want to assign them into any cluster. Okay, so that's the general idea of density-based clustering. So down here, there's a MATLAB link showing you one example of density-based clustering and why it's an important algorithm to know. Is because it is able to handle arbitrary cluster shape. So in this case, we have two clusters. One is the one in the center. The other is this ring here. If we do density-based clustering, the algorithm is able to say the center is one cluster and the peripheral rim is another cluster. But if we do k-means, then k-means will completely mess this up because k-means really the way that cluster center is defined. Okay, so and now that you hear kind of two different algorithms that have different caveats, right? So k-means is prone to be is prone to error when you have clusters of weird shape, but k-means will perform better when you have clusters of round shape, and density-based clustering does not have this problem. Okay, so another algorithm, well, in the interest of time, I'll skip it, but just let you know the reference. This is a science paper published, well, not too long ago. And what they're doing is also they're looking at local density of each data point and then try to say identify data points whose local density is high, and also they are far away from other data points whose local density is higher. Okay, and those are kind of cluster peaks or little hilltops that are far away from other hilltops basically, and those are likely to be cluster centers. And the basic idea is actually very similar to the DB-scan algorithm on the previous slide. Let me skip this, okay, and just show you a link of a well, also MATLAB tool that implements this density-based algorithm and quickly show you its result. So given a data set looking like this, where there are these clusters of different shape and also buried in some noise, okay, the algorithm is able to label these clusters with colors, and then these sort of noise points, these are the unlabeled points that the algorithm threw away. Okay, so at least in this example, density-based clustering performed really well. Okay, all right. So take-home message about all these 5 clustering algorithms so far, okay, is that while hierarchical clustering, I think, is a very popular algorithm, it gives you, it induces this tree structure and ordering of rows and columns so that you see these blocks, and these are very easy for you to interpret, say, marker genes or signatures for different types or clusters. Okay, so for visualization purpose, I would say hierarchical clustering is the best one to go with. And k-means is super simple, right? And very cheap to compute. So it doesn't really take you much effort to do it, so why not, right? But of course, there is this caveat that k-means assume different clusters to be roughly of similar size and of round shape, okay? So if k-means doesn't work, then one thing you should check is, maybe some other algorithms that does not have this round shape assumption. So community finding works really well if the graph, right, the weights we construct are sort of properly defined. And also community finding does not make any assumption of shape of clusters. Okay, so it's in that sense better than k-means. And also it is more able to catch rare clusters, and is very popular in the single cell literature, Louvain or Leiden, for example, right? And also, even when the dimensionality of your data is high, community finding usually still works okay. Again, depending on like how you define the graph, how you define the weights. All right. So density-based clustering, okay. Its advantage is, again, it does not make any assumption of shape and size of the clusters, okay. And it also can catch rare clusters, okay. But the caveat of it is that density-based clustering depends on the densities we estimate, right? And usually in data with very high dimensionality, okay, and let's say 50 dimensional, and we only have a few thousand data points. So in those cases, usually our estimation of the local density of each data point is very poor, okay? So really for density-based clustering algorithm to work well, we need the dimensionality of the data to be very low. I would say to be, say, 2-dimensional, 3-dimensional, 5-dimensional. If we start off with very low dimensional data, or if we are able to reduce the dimensionality to that low in a way that we trust, then density-based clustering is appropriate. But if we only reduce, if the dimensionality of the data is higher, say 20, 30, 50, 100, or even higher, then density-based clustering usually will not work that well. And I would go for community finding, or also try simple k-means. Okay, so among these algorithms, these are kind of my internal thinking process or pipeline of which algorithm I choose to use. Okay, so I have another 5 visualization algorithms prepared, but in the interest of time, I'll just stop here and leave the remaining 5 visualization algorithm to the next lecture. All right. So let me stop recording.
Actually, there's a couple of questions, Pong. If you might want to answer with the.
Okay. Yes. The questions. Let me read them. So I'll just go backwards. So one question is, what is the importance of clustering and what represents for clustering? Well, I would say in the context of gene expression analysis, the importance for clustering is to define kind of operational subtypes. Okay, and of course, I mean, in different contexts, operational subtypes carry different meanings. So for example, if we are looking at a bulk RNA-seq data set of cancer patients, and if we try to cluster the patients into different patient clusters, okay, then these different patient clusters, they may have different survival outcomes. They may respond to different drugs in different ways. So that, if later we realize that, say, one cluster of patients respond to a certain drug really well, but the others do not, then this operational subtype is going to help us to inform how we can personalize treatment strategies for different clusters or different types of patients, right? And now, if we are thinking about single cell analysis, where our data matrix, each column is an individual cell, then when we cluster the cells into cell clusters, right? And these cell clusters, they potentially could correspond to different cell types and even cell subtypes or cell states that we didn't know before this analysis, right? So for example, maybe we do clustering of a PBMC data set of immune cells, and we see a cluster of 100 cells, and they show very special gene expression pattern for certain combination of marker genes that's different from what we know before. Then maybe this particular cluster represents a new immune cell type that has a special set of functions. And later, that can be a hypothesis, and we can try to identify protein markers that can help us to flow sort these cells, and then followed up with functional assays to see whether this particular cluster really represent a functionally distinct novel cell type. And that can help us to kind of deepen our kind of knowledge of the basic biological science, right? And there also, of course, is a possibility that we can cluster the genes, right? So given gene expression data in some context, maybe again, a certain cancer, right? We have many patients worth of data, and we can ask which genes are, say, correlated, they go up and down at the same time, right? So we can hypothesize that these genes, they belong to the same pathway. And if this pathway is very strong, show very strong correlation in cancer data, but then these genes, they are not correlated in normal patients, then we can form a hypothesis that, you know, somehow the interplay among these genes is important in whatever process that this cancer employs, right? And that can help us to maybe derive hypotheses around mechanisms of, say, how this cancer operates, and later also conjectures on what drugs may be able to target on that process and hopefully improve patient outcome, right? So when we do clustering, I would say that you know, we can cluster patients, we can cluster cells, we can cluster genes, and in each of these sort of practice, the resulting clusters may help us to generate some hypothesis of, you know, new biology knowledge that we can pursue, and that's, in my opinion, why clustering is important, an important type of analysis. All right, Greg, anything you want to add?
No, that's good. That's yeah, I mean, I use it just to help look at the overall structure of the data. I mean, hierarchical clustering, I actually use Ward's clustering a lot. It's a good way to visualize the main effects, but as you'll see later on, for single cell data analysis, hierarchical is not really useful. I don't use k-means very much. Sort of not that common in the field. But yeah, I agree with your thoughts about the importance of it.
All right, so there's one more question from Justice about comparison between spectrograph analysis, where we use eigenvalues and eigenvectors, and community finding. Okay, so spectrograph analysis, its advantages is really easy to implement. Okay, its disadvantages, every time you run it once, you only get 2 clusters. If you want to get more clusters, you have to run it in an iterative way, and then you have to define your stopping criterion. For example, the minimum size of the clusters, or, you know, the expected differences in between the 2 pieces the petition generates as stopping criterion. Okay, so, and that makes the implementation a little bit complicated. Now, community finding, the concept is easy, but indeed, you know, to really optimize the modularity quantity queue, it is an NP-hard problem. So I would say, if one's goal is to, say, implement community finding in a perfect way to 100% optimize queue, then I would say that's a very difficult task, or even an impossible task, and I would never try to do it. Okay, but now in the literature, in the computer, especially the computer science literature, people have already developed efficient implementations, such as Louvain and Leiden algorithm, that can help you to get close to the optimal queue, right? So, so that you know, it's just very easy to use. So to me, I think one good reason why in the literature community finding is popular, okay, is actually because there are good algorithms that are already well packaged for people to use. If really, you know, every time you apply community finding, you have to implement Louvain yourself. If that's the case, I think very few people will use it. Okay, so in between spectrograph petitioning and community finding, I think they're actually very similar to each other, and I would say the ease of use is why people prefer community finding algorithm, and also like definition of what in spectrograph petitioning, right? Definition of stopping criterion. Usually there are multiple definitions that you can choose to use, and exactly which one to use. Also, I mean, it just have larger space of tuning that make the whole thing more kind of difficult to use. All right, so my computer is acting a little bit weird, but I hope I'm still here. and you guys can still hear me.
Yes, we can still
Right.
hear you.
Good.
but
So
blue
let me
screen.
stop sharing and also stop the recording.
Hmm.